Alright, section 8.5, properties of sound waves. So let's get started. So when we talk about sound waves, we tend to think with our general human focus that sound is everything that we can hear, but sound is a lot larger than that. Okay, humans can hear from about 20 hertz to about 20,000 hertz, and as you get older, that 20,000 top end starts to drop off quite quickly. Myself, at present, I can only hear to about 16,000 hertz, whereas young people like yourselves, you can hear all the way up to 20,000 hertz. Okay, so we have an effective range from about 1,000 to 5,500 hertz, and then we have some regions that are beyond our hearing, and we give them names, and you've probably heard terms like infrared and ultraviolet. Well, infra, okay, is a way of saying below, and ultra is a way of saying above. So if you look at this one here, ultrasonic or ultrasound, this is above. And infra means below. Now that doesn't mean that sound doesn't exist, it just means that we can't hear it. And that's a really important concept to grasp. It's just a quick visual of what animals can hear. Elephants, you can see, can hear most of our range, plus they can hear lower frequencies. And there are a lot of things out there that, animals in particular can hear higher frequency. Dogs in particular, dolphins, bats, they just have a wider range or a higher range of hearing than we have. So you may have heard the term ultrasonic. We use ultrasound for a lot of medical reasons. You can do ultrasound if you have an injury, stimulates blood flow in tissues. You can also do ultrasound imaging. So this is an example of a way to inspect or investigate the health of a fetus, which is important. Okay, so you can see in this particular picture, you can see quite clearly a head, and little legs, arms, and all those types of things. And so you can do a lot of investigation without actually having to do surgically cutting or things like that. It's a way to get a picture inside. You can do a lot of different organs and damages and different things. So if you're on the health schism or on that direction, ultrasound is something you're going to encounter. On the bottom here I have something called the electromagnetic spectrum, and again you'll see infrared and ultraviolet. So infra means below, so just like we can hear a range of sound, we can only see the visible spectrum. It doesn't mean those are the only electromagnetic waves out there, it just means we can only see visible. We can feel infrared, we can feel ultraviolet. Ultraviolet is normally tied to your sunburn issues. X-rays you don't feel, but we go for X-rays for our teeth, our bones and things. And these are not what we would call mechanical waves, but they do have a lot of wave properties. So you'll see ultraviolet, we're starting to see high frequency, shorter wavelengths. Infrared, you're looking at lower wavelength, lower frequency, lower energy. So they have a lot of wave properties, but they're not technically mechanical waves. Okay. All right, so let's look at something called the speed of sound. Now, in our last lesson, we talked about the temperature of a gas affecting its speed, and we said, logically, you'd think a cooler gas would be denser, that acts more like a solid, so it should be more efficient. But we said it's converse, it's opposite to what you think. Hotter, warmer gases are actually more efficient at letting mechanical waves and energy pass through them, which means they're faster. So if you look at this expression, the speed of sound is 331.4 meters per second, and then it has this piece right here. Okay, and that is an adjustment based on the temperature of the gas or the air that you're traveling in. Okay, so this is the speed of sound in some sort of air. We're not talking about liquids right now, this is just in air. Okay, so if you had a higher temperature, that would increase the speed of sound, whereas say if you had a negative temperature on a cold day, it would subtract or take away this piece right here from that 331.4. Okay, so just a little calculation validation of that concept. So let's take a quick look. Determine the speed of sound at a certain temperature. The temperature outside is 23 degrees Celsius. So we work in Celsius for this expression, not Kelvin, not Fahrenheit. What is the speed of sound in air at this temperature? So we'll take our expression, and where we see the T right here, we put in 23. Okay, so you take your 0.6, oops, clear that out, 0.606 times 23, and you add to that your 331.4, and you should get a new velocity of 345.3 meters per second. Okay, not an overly complicated calculation. The key piece though is keeping track that this is in Celsius and keeping track of whether it's positive and negative. Okay, so the speed of sound is measured to be 318 meters per second. What is the current air temperature? Okay, so if we take that same expression written right here and we replace V with 318, and now we're solving for T. Okay, and I'm not going to do all of those steps, but you can see pretty quickly this should be a negative number. So if we subtract the 331.4 from both sides, you can see there's the negative. Now if we divide that 13.4 by 0.606, we should get a negative 22.1 degrees Celsius is the ambient air temperature. Okay, so you can pause it here and you can try those. I'm not going to go through them all. I'm sure you can handle that expression. So just pause it, take a quick try. Okay, so the first one, if the temperature of the air in your region is 32 degrees Celsius, what is the speed of sound in air at that temperature? So you would multiply 32 by 0.606, add it in, so 351 meters per second. If the speed of sound near you is 331 meters per second, what is the ambient air temperature? So again, just the example we did. Subtract 331 from 333, divide by 0.06 or 0.606, so 2.64, so close to 0. Okay, so because there wasn't a big change in that from 331 to 333. And then if the speed of sound near you is 350, so we would expecting the ambient temperature to go up because the speed of sound has gone up, and it has. Okay. All right, Mach number. This is usually associated with airplanes, spacecraft, those types of things. A couple of key things. Mach number is just a ratio to give you a number that expresses how many times faster than sound you are. Okay, so M is unitless. So when we say Mach 3, that means you are 3 times the speed of sound. Okay, so you'll notice here you have airspeed of an object on top divided by the speed of sound, and the local piece means you do have to incorporate the temperature into your calculation. Okay, and here's the big piece. The speeds must be in the same units. And what's cool about this is it doesn't matter if they're both in kilometers an hour or both in meters per second. What you can't have though is the kilometers per hour over a meters per second. That's a big error. Okay, so as long as they're in the same units, then you can calculate this pretty quickly. Okay, so Mach 1, Mach 2, Mach 3, that's the speed of sound, twice the speed of sound, etc. Okay, so just to give you a couple ideas of what the speed of sound in different medium can be. So in air, this is what we're most familiar with. You'll see a range from 319 to 344 meters per second. Now, if you move to something that's a solid, and that's that stronger intermolecular bonds, that's more efficient, it's faster, and you see a ginormous jump. Okay, for steel, glass, you get a giant, almost, I don't know, what's that, 20 times greater? Okay, approximately. So that's a big increase in the speed of sound inside of a solid. Okay, and then if you go back to water, you're looking at about 5 times greater. And then wood, maple, you're talking instruments, those types of things, back up to 4,110. So a fairly large jump. Okay, so let's try one. An aircraft is flying at 905 kilometers an hour and an air temperature of negative 50 degrees Celsius, so they're in the upper atmosphere. Calculate the Mach number associated with this speed. Okay, so here's the first problem. 905 kilometers an hour. Our calculation for the speed of sound is in meters per second with the temperature. So we're going to have to do some converting here, no matter what we do. Okay, so if we put in the negative 50 for the temperature, we get a new temperature of 301.1 meters per second. Now, we can convert that value to kilometers an hour, or we could go and convert the 905 from kilometers an hour to meters per second. It doesn't matter, we just need the same units. So in this one, they're going to convert the 301 meters per second. Okay, I'm going to leave that alone at meters per second, and they're going to convert the 905 kilometers an hour. So you can see right away you have a speed of sound of 301, speed of the object at 251. So we're expecting a Mach number here that's less than 1. Okay, and we end up with 0.835. So the Mach number for this object is 0.835. It's less than the speed of sound because it's less than 1. So if you want to pause it here and take a try, 3 little questions. I will take up these ones fairly quickly. So have a pause and take a look. Okay, so of the local speed of sound, let's do number 1 first. The local speed of sound is 344 meters per second, and the aircraft's flying at 910 kilometers an hour. What is the Mach number? So we have to convert these for sure. So quick refresher on converting. Let's just turn this into kilometers an hour. So we know that 1 kilometer is 1,000 meters, and there are 3,600 seconds in 1 hour. Okay, so this is the multiplying by 3.66. Sorry, 3.6. So I get 1,238 kilometers an hour is the speed of sound. Okay, so now if I have my Mach number, because they're both in kilometers an hour, I can just go 910 divided by 1,238, and I get 0.74 as my Mach number. 73, pretty darn close. Okay, get rid of that one. We'll try the next one. If the Mach number, so number 2, if the Mach number is 0.93 and the local speed of sound is 320 meters per second, what is the speed of an airplane in these conditions? Okay, so again, you have the velocity of the object, the velocity of sound. So we have 0.93. We have the velocity of sound is 320. So we need the velocity of the object. So if we multiply those two together, 298, they'll probably say 300 for their answer. So they have 300, and they converted it to kilometers an hour, which is fine as well. Okay, now the last question, number 3. If the Mach number is 0.81 and the speed of an airplane measured by radar is 850 kilometers an hour, what is the local speed of sound in kilometers per hour? Okay, so if we set that up, Mach number, velocity of object, velocity of sound. So we have 0.81. Velocity of the object's 850 kilometers. The velocity of sound. So we have to do a little rearranging. And if we do that, 850 divided by 0.81, it's about 1,049, so I suspect they'll round it off to 1,000. And that is in kilometers an hour because that was the measurement of the 850. So if we go just up here and do a quick check, they got about 1,000. Okay, so we're on par. Okay, now speed of sound in various media. We've talked a little bit about this. Rigid intermolecular forces, solids are more efficient, they're faster, and waves go further in them. Now, If we move to something called sound intensity, okay, so our loudness depends on our sound intensity. Okay, so now sound energy is a longitudinal wave, and that the amplitude of a longitudinal wave is a difference in pressure. Okay, so when we talk about sound waves, if you take a cookie sheet and you ripple it, you'll hear a large sort of thunder crack. Okay, and it's the difference between those pressures, okay, that gives you that sound, or how loud that sound can be. Okay, so generally we take the amplitude of the wave as a measure of how much energy the wave is transferring. Okay, so if you look at something like this is pressure expression right here, and pressure is defined in a whole bunch of mechanics sections. It's just a force per unit area. So this on top, this F is a force and over a unit area. Okay, and we're going to avoid a lot of the math for sound intensity because it involves something called logarithms, but there's no reason we can't talk a little bit about what's going on. Okay, so the larger the amplitude, the larger the difference in those pressures, the larger the sound is to you. Okay, and that's sort of one of those basic ideas. So the amount of sound energy being transferred per unit area, okay, is called the sound intensity, and it's measured in watts per square meter. Okay, and what we're going to look at when we talk about sound intensity, okay, so watts is a measurement of power, as we know from our energy section. Area, we're going to use square meters. So we have joules per second for power. Okay, area we're going to measure in square meters, and this is the part where we're going to expand our idea of area. So if you have this little dot here, if we imagine sound, it goes out in concentric circles like this. Okay, so when we model this area value, and this is really important for IB folk, we're going to imagine the sound emanating out in all directions. So our area is going to be tied with pi r squared. Okay, and that's going to come up in multiple topics in grade 12, so I just want to sort of lay that foundation for that now. Intensity is equal to power over area, and area is going to be related to that circle shape. At this stage in grade 11, we don't do a lot with it just because our math skills aren't as high as we need. You need grade 12 math to do some of the math. Okay, so you can see right here, here's logarithms. That's a grade 12 concept. Okay, now decibels is a measurement of our sound intensity. Okay, so now decibels are, they're zeroed out at what we can consider the smallest amount that humans can hear. Okay, so it's kind of arbitrary. We've chosen ourselves to be the benchmark, and then we measure from there. Okay, so when you see the next slide here, 0, which is sort of arbitrary, is the threshold of human hearing. Okay, so you have a sound intensity right here, and we've called that a decibel level of 0. And again, we're not going to explore the math. We're just going to talk more about the effects than anything. As the sound level or the sound intensity increases, the loudness increases. So if you look down this side here, all of these things should be louder. Okay, so an empty classroom to an alarm clock to a motorcycle, and you'll notice they're giving distances for all of them, because the closer you move to an object, okay, that's going to affect the intensity and the energy you experience from that sound. Now this is an important piece here, threshold of pain. There is a limit to your hearing, so that when you are exposed to a certain amount of energy, you can damage your ears. Okay, and you will be driven back by some of these things. If you've ever been to a rock concert and you've left with your ears ringing, you've actually done damage to your ears, just so you know. Some of these things you will not be able to take. You could not stand close to some of these things. You would be lying on the ground writhing in pain. Okay, so loudness and distance. You can see a little graph here. As you move back, because we're talking about that area, so if this is that little dot, and if we imagine, see if I can draw a decent picture here. You can kind of see this area here is smaller than this area here, so we have to take the same amount of energy and kind of disperse it over a larger area, so that intensity starts to decrease. Okay, and I'm going to erase that because my artistry is not very good. Again, the key piece we want to take away from this though is as you move farther away, the sound level drops. Okay, so the intensity starts to drop off. That energy goes down. Why that's important to you in grade 11 as you move out into the workforce. This is really important. So if you are mowing a lawn, if you are working in some place noisy, you can only allow yourself to be exposed to a certain decibel level for a certain period of time. Okay, so if you have 100 decibels, after 15 minutes you're starting to do permanent damage to your ears. So if I jump back here for a second, 100 decibels, jet flyover, rock band, motorcycles in that area. When I held up my sound meter when I'm doing my lectures in class, I'm about 70, 80 decibels. When you're right in my face, you don't sit that close, so that's good, because that would limit how long I can talk to you at that particular intensity. Okay, so you can start to see though at 85, if that's my level, I could talk to you for 8 hours and I wouldn't damage your ears. Ha ha ha. Okay, but down here you get less time. So the louder an object is, the less time you have before you do permanent damage. Oops, jump through 2 there. So the big things to take away from this is our hearing range. This is the speed of sound. Those are the calculation and sort of important numbers. And then in terms of self-protection and keeping your hearing working properly, you need to understand what decibels are in terms of a certain amount of energy is going to reach your ears, and if you don't control that with earplugs or ear muffs or whatever they're called, ear protection of some kind, you can damage your ears. Okay, so we'll leave you with section 8.5. If you could try 2, 3, 5, and 10, that would be awesome, and thanks for tuning in.